Welcome everyone to this series of lectures on using autoencoders on image data. We've already seen that even simple images are actually high-dimensional datasets. Recall that the MNIST dataset, or even the Fashion MNIST dataset that were simple 28 by 28 images, that actually contains then 784 features. And we can think of each of these features as a dimension. So each particular pixel is a dimension of data. So we have 784 features. It might be a good idea to apply autoencoders to this sort of data set. So what we could do is start off with a very simple premise. We're going to take our original image, pass it through an autoencoder, and then have the autoencoder attempt to recreate the image as the output. So essentially what it's going to do is it's going to attempt to learn what pixels are important as it encodes it down to a smaller hidden layer, and then it's going to use those important features to attempt to reconstruct it in the decoder on the output. So recall that those hidden layers get smaller and smaller. So it's going to have to learn which pixels are actually important for identifying an image in order to reconstruct it as the output. So then we would now have an autoencoder that understands what features of the 784 pixels are important and which are not. For example, it will likely understand that pixels on the edge don't really matter. In fact, if we take a look at a variety of the MNIST digit dataset images, you'll notice that the very first couple of rows at the very top, and really all the pixels around the edge, usually don't contain any useful information because all these numbers are centered in the image. So hopefully the autoencoder would learn that those particular pixels are not very valuable. Now what we could do is do what we just did in the previous lecture and then just cut this autoencoder in half and then see what we could do with dimensionality reduction. We could then plot this dimensionality reduction down to maybe 2 neurons or 3 neurons, and then plot out the number classes in this reduced dimensionality space and explore what numbers are similar to what other numbers. But in a real world case, this isn't super useful because you already have that image data to begin with. So it's an actual use case we could work with for image data that also involves autoencoders. Well, what we can do is we can use this same logic to create an autoencoder that actually removes noise. And we know that noisy images are definitely a real world problem. So what's going to happen here is the autoencoder will learn what features are important. So what we're actually going to be able to do is using an autoencoder, we will feed in a noisy version of our number. So we already have these clean numbered data sets. So we have the MNIST data set, all the numbers are clean. And the autoencoder, what it's first going to do is, as it takes in its input, it's going to add in noise. So here we can see on the left-hand side, we have a noisy version of that number 7. And then it's going to encode as we go deeper into these smaller hidden layers. And it's going to hopefully be able to learn what pixels are important and which are just noisy in order to reconstruct the correct number on the output, since we'll be comparing that output to the real number image. And then we now have an autoencoder that can actually denoise images. So we're going to explore 2 autoencoders. We're first going to attempt to recreate the very first simple autoencoder that just recreates input images in the output. So it just takes in an image and then encodes it and expands it back out, and we'll see how well it can do at retaining information as we reduce the number of neurons. The second thing we're going to do is build the actual application autoencoder, which removes noise from input images to accurately reproduce output. Let's get started by heading over to a notebook and attempting to create that first autoencoder. I'm going to jump to that notebook now. All right, here I am at my notebook. I've already gone ahead and imported pandas PD, numpys np, and matplotlib. And the other thing I did was I also said from tensorflow.keras.datasets import MNIST, and I loaded up the MNIST dataset just as we did during the convolutional neural network section of the course. So you can recall that you can use plt imshow to show any of these images. So let's just grab the first training image, run it, and here we can see it was a 5. All right. So what we're going to also do is quickly scale our data set. And recall, just as we did in the convolutional neural network section of the course, we're going to say xtrain is equal to xtrain divided by 255. And we'll also say xtest is equal to xtest divided by 255. Okay. So we're already very familiar with this data set, so we won't really cover it in more detail. Instead, let's move on to actually building out our basic autoencoder. We'll say from tensorflow.keras.models import sequential, and then from tensorflow.keras.layers, import dense, flatten, and reshape. And then we'll also use the stochastic gradient descent optimizer as we did before. We'll say TensorFlow, keras.optimizers, go ahead and import SGD. Okay, now keep in mind, there's no right or wrong way to build out this autoencoder because this falls under kind of a semi-supervised learning process. Because at the end of the day, there's no kind of super correct answer as far as what the encoding should have been exactly. So what we're going to do is we're going to build what's known as a stacked autoencoder, which means there's actually multiple stacked hidden layers that slowly reduces the dimensionality of the data set. So what we can do is we understand that we have 784, essentially 28 times 28 pixels, right? And what we're going to do is we'll just keep dividing this in half. So we'll go from 784 to maybe around 400, since this is equal to 392. So we'll go from our encoder, start with a sequential, and then the other thing you should recall is if we take a look at the very first image, or the way these images are constructed, they are actually still retaining their shape of 28 by 28. So the first thing we're going to do is we're going to flatten this out. We'll say encoder add, and we're going to first flatten this out, and we'll make it aware that the input shape is 28 by 28. So you could always adjust that input shape to fix whatever dimensions you're working with for your own images. So we first flatten it out. So we have it now 784. And then what we're going to do is we're going to add in a dense layer that goes from 784. And let's go ahead and cut that about in half to 400 neurons. And we'll set our activation function equal to a rectified linear unit. And we're going to keep doing this in order to make this a stacked autoencoder. It's probably too much to ask to just go from 784 down to something like 25 dimensions. So we'll do this slowly. That way the encoding half of the autoencoder can actually attempt to kind of slowly learn this dimensionality reduction. So then we'll go from 400 to 200, and then let's cut that in half again. We'll go from 200 to 100, and then cut that in half again. We'll go from 100 to, let's say, 50, and then let's go ahead and do that one more time so that we go down from 50 to 25. Okay, and again, this is kind of just an arbitrary choice of how far down we're going to go here. So now I'm going down from 784 to 25, which if I think about that in terms of a percent, I'm actually going down to just 3% of the size. So I'm going from 784 dimensions down to 25 dimensions, which is around 3.2% of the original feature size. So we have 784 dimensions, we're going down to 3.2% of that, which is 25 neurons. So this is kind of impressive already, especially if it's able to recreate after it goes through the decoder. So let's build out our decoder. Just as we did before, we'll use a sequential model, and then we'll say decoder add. It's going to take in dense, and here we're essentially going to build out the reverse of the encoder. Keep in mind, we're not going to duplicate this very last one because that's the center hidden layer. So the very first layer in the decoder should match the second to last layer in the encoder, which is going to be 50. So right in the middle, it's going to have that 25 neurons and then expand back out to mirror the encoder. So then it goes from 50 here, and then what we're going to specify is the input shape is equal to 25. So that kind of shows the connection here between the encoder and the decoder. So we have that input shape is equal to 25, and then finally, let's say that the activation function is equal to a rectified linear unit. Okay, so that's the very first layer in the decoder, and now we're just going to mirror our encoder. So we'll add in another dense layer, and then we'll go back out to from 50 to 100, and say the activation function is a rectified linear unit, and then I'll just copy and paste this and expand it back out to the original 784. So 50 to 100 to 200, add in one more, 200 to 400, and then finally we'll go from 400 to the original, which is either, you can type out 28 times 28, which is okay, or you can say 784. The important thing to note here is that this activation is going to change to sigmoid. And the other important thing to note here is we need to compare this to the actual original images. So we'll say decoder, add, and we're going to reshape this to be 28 by 28 in order to successfully compare the input of 28 by 28 to the output that should also be 28 by 28 after going through the autoencoder. And the reason we have sigmoid as our final activation function is because we essentially are performing a binary cross entropy loss at the end of our autoencoder. We're just checking, does the final output image after going through the entire autoencoder match the true image that we suspect it to be? So what does that actually look like? Well, we take our autoencoder and build it by saying sequential model, just as we did before, and we pass in the encoder and the decoder. And then to compile it, we'll say compile, and loss is equal to binary cross entropy. And it's binary cross entropy because the autoencoder doesn't really care how many distinct types of numbers there are. It doesn't care that there's 10 classes of numbers. All the autoencoder cares about is the image I'm producing at the output going to match the image that was originally put into the input. So that's why it's just sigmoid and binary cross entropy. And then we'll go ahead and specify our optimizer. And this is something you can play around with, especially for your own data sets. So that's why we use stochastic gradient descent. And you can play around with that learning rate. Then you can always slow down your learning rate by giving a smaller value if you notice your reproductions are pretty off. Or if your training is taking too much time, you can always experiment with increasing the learning rate by giving it a larger value to hopefully learn faster. So we discussed that in our original theory lectures all the way towards the beginning of this course. And then finally, let's go ahead and keep metrics, and we're going to keep track of accuracy instead of just our loss. So there's our accuracy. And then finally, we'll say autoencoder, and let's go ahead and fit this model. We're simply going to pass in xtrain and xtrain. And again, the actual train test split is kind of irrelevant here because this is just an autoencoder. And this is why, again, it's called a semi-supervised learning process, because it's not like we're trying to actually perform some sort of classification task here. Instead, all we're trying to do is see if this autoencoder is able to learn what features are important as it encodes the information to a smaller dimensionality. Remember, it's just 3.2% of the space with 25 neurons, and then expand it back out. So that's why it's just passing in xtrain, xtrain. When we pass in fit, that's really both the x and the y. It's just, is the image number 1 equal to image number 1 from xtrain? Okay. So then we'll go ahead and train this for, let's say, 5 epochs. And what we can also do is pass in validation data. So if you want to just check its performance, so to speak, on data it's not actually being trained on to reproduce, that's what you can do with the test set by saying xtest, xtest. But again, that train test split is not a fundamental part of this process. So we'll go ahead and fit this, and I'm going to fast forward in time until the autoencoder is done fitting. All right, this finished training for me. Now let's go ahead and see how we can use the autoencoder and take a look at what the images look like after they've been passed through the autoencoder. So what we can do here is we can say past images, and let's go ahead and just grab a batch from the test set. We'll say autoencoder predict and say xtest. Go ahead and just pass in if you want 10 of those. And so what we're doing is we're passing 10 images that the autoencoder was not trained on, and then we're asking the autoencoder to quote-unquote predict. And predicting for this autoencoder really just means attempt to reconstruct the image after reducing its dimensionality down to 25 neurons. So let's see how well of a job it did. First, let's go ahead and view what one of the original images looks like. So we'll say plt imshow And in fact, let's do a couple things here. We'll say n is equal to 0. So that's something you can play around with. And we'll show why in a second. We'll say plt imshow, and then we'll say from xtest grab n, and then we'll say plt show here, and right below it we'll say plt imshow, and we'll say is passed images of n. And let's add in a little label here. So we'll print out original image, and then we'll print out attempted reconstruction of it. And this is technically after it's gone through the entire autoencoder. Again, what we're doing here is we're comparing the original image and what the image would look like after being passed through the entire autoencoder. So we're doing this just for the first image for N0. Run that. So here's our original image, 7, and this is what it looks like after being reconstructed. So is this impressive or not? Notice the 7 looks a little blurrier, but you should realize here that this is actually extremely impressive, because what the autoencoder was able to do is it squeezed down the 784 features or dimensions down to just 25, and then was able to then expand that back out to recreate what essentially looks like the original image. And this allows you to then play around with the value of n. We can choose another one. Let's say n is equal to 3 to check out that third image. And here is the original image, looks like a 0. And then here it is after being passed through the autoencoder. So you can see that the autoencoder is almost acting like kind of this blur functionality where it's just checking what it looks to be important in order to reconstruct the image. What we're going to do in essentially part 2 of this lecture series is build out an autoencoder for denoising images. So we'll continue right where we left off in part 2. I'll see you there.